Hello, I'm Mr. Bob, and welcome to my Geometry Review video series. This video covers Chapter 12, Section 4, titled Compositions of Reflections. By the end of this video, you will have reviewed recent lessons on recognizing a composition reflection, on the composition of reflections in parallel lines, and on the composition of reflections in intersecting lines. And finally, you will review the procedures of finding a glide reflection image. If you'd like me to cover any of these topics in greater detail, please leave your request in the comment section below. Please subscribe to this channel if you find the video to be helpful. Thank you. So let's start this review off with a definition. It says a glide reflection. A glide reflection is a composition of glide translations and a reflection in a line parallel to the glide vector. A glide reflection is a composition of a glide translation and a reflection in a line parallel to the glide vector. Okay, objective 1A, compositions of reflections. And this is objective 1A because there are a couple more slides that'll eventually follow this one that are still from the objective category here. If two figures are congruent, there is a transformation that maps one onto the other. If no reflection is involved, then the figures are either translation or rotation images of each other. So either they're sliding them around, right? Translation or rotation. So if you have these two congruent figures, as you slide them around, they're going to eventually match up, right? Unless there's a reflection involved, which flips it, for, like, say, from its back to its front, kind of a concept, okay? Okay, example 1, recognizing the transformation. The two figures at the right are congruent. Is one figure a translation image of the other or a rotation image? Or neither? Explain. Well, as you look at that, is it a translation or a rotation? Well, it's certainly, this is the orientation of these congruent figures do not appear to be opposite, right? So they're not flipped. There's no flip involved. There's no reflection involved. It's still the same figure. It's just like slid or rotated, right? So, one is a translation image or a rotation of the image. Clearly, it's not a translation image. Why is it not a translation? Because in order to get from the 5 would have to have been slid to the right in the same orientation. It could have gone up and down, but there's also a rotation. So this is truly a rotation image. So it's moved and it's rotated. It's a rotation image. Okay, the example 1, check your understanding. So what they'd like you to do here is to pause the video and think about this, or maybe you don't have to pause, but I'll wait until you come back. The questions are, it says, the two figures are congruent. Is one figure a translation image of the other, a rotation image, or neither? Explain. Okay, I'm going to assume that you've made your decision on that. We're going to talk about it. Well, it's obviously these are opposite each other, right? Because there was a reflection or like, see, there's no way you can turn the image on the left in any way to have it be upside down, so to speak, or laying on its belly. So there was actually a reflection that has gone in here. So it's neither is the answer to this. Okay, objective 1B, compositions of reflections. So this is that second slide I was mentioning earlier that would be showing up in the review of objective 1. So it says, if two figures are congruent, there is a transformation that maps one onto the other. If no reflection is involved, then the figures are either a translation or rotation of each other. Okay, so if you don't flip them, then they're either being translated or rotated. Okay, any translation or rotation can be expressed as the composition of two reflections. So we're going to see that coming up here. It's pretty interesting to see this. So a theorem 12.1, a translation or rotation is a composition of two reflections. In short, that's saying that you can, depending on how you set it up, you can do two reflections to do a translation and or a a rotation. You flip one, reflection flips it over and changes the angle on it possibly, and then flips it again and it comes back right side up and it's facing the correct direction, and it looks like a translation or maybe a rotation depending on what you're trying to do. So let's see what comes up. Okay, so it says here two examples that illustrate theorem 12.2 and 12.3 suggest a proof of theorem 12.1. How to find two reflections for a given translation or rotation. So it says theorems 12.2 and 12.3 together form the converse of theorem 12.1. So we'll see what that's talking about here. Theorem 12.2. A composition of reflections in two parallel lines gives you a translation. A composition of reflections in two intersecting lines gives you a rotation. So if the lines that you're reflecting over are parallel, you're going to get a translation. If the lines are crossed and you're doing a reflection across these two cross lines, it'll end up being a rotation and not a translation. Okay, so let's see how that shows up here. Okay, example 2, composition of reflections in parallel lines. So here we're going to see, it says describe the resulting translation. Here we're going to see these two reflections are going to be a translation. So you see in the beginning here, the parallel lines are L and M, right here. Line L and M are parallel. And there's an angle to them. So you're going to see like a downward shift is going to happen. You see, if you look at the last picture, you see the downward shift. It's like a translation. However, what we're talking about here is to see that when you flip the R across the first line, line L, you get this R that's upside down. It's not the same, right? It's inverted. It's R. But here it was a regular R. Now it's on its face, and it's got a little bit of an angle because of the parallel line kicked it down. And now you're going to reflect. You're going to go again. This is reflecting in L. Then you're going to reflect that same inverted R now across the line M. And when you do that, it comes back right straight up, and you end up with the R over here. So you started with R like this, and you end up with R over here, and now you've got a translation between the two. And the distance it traveled is based on your parallel lines, okay? The R is translated the distance and direction shown by the green arrow. Well, that's this arrow right here. The green arrow right there. Here's the green arrow. I did it in blue. The distance and direction shown by the green arrow. The arrow is perpendicular to lines L and M with length equal to twice the distance from L to M. So the distance that it translated, as you look at the distance between L and M, this distance here, L and M distance, and double it. So R moved from here to here, and that distance is twice the distance of the parallel lines. But of course, R has to end up, when the first flip, it has to be between the lines. When you flip it across the first line, it has to still be between the two lines. Okay, now the next we're going to look at the crossed lines. Okay, but before we go on to the cross lines, we're going to do a check your understanding for example 2. It says draw the line L and M as shown above. Well, I've drawn it here, so you don't have to draw it. So you see what you're looking at here. It says draw R between L and M. Find the image of R for a reflection in line L and then in line M. Describe the resulting translation. Well, this is going to be interesting. So go ahead and try it. When you come back, I haven't tried this myself, but we'll see how it turns out when we look at it when we come back. So go give it a try. Okay, we'll assume that you've done that and you're back. So let's make it as simple as possible. I'm going to draw it so that my R is somewhere in here. Oops, okay, there's my pencil. I'm going to say that my R is somewhere right in here. I'm going to draw a nice R. Okay, and my R is kind of vertically parallel with the lines, so to speak, right? So it says first it says to draw are between L and M, then find the image of R for rotation in line L. So then what you're going to do is you're going to go like, we're going to end up going across line L, and it's going to invert, correct? It's going to go like this. It's going to be down here. Sorry for my squiggly lines. So now the R is backwards, and we've gone this distance, whatever that distance ends up being. It's actually whatever the distance you are from the line L to the, say, the center or whichever the edge. It's the same distance across the other side. Then it says for the image R reflecting in M. So now we're going to take this R here and reflect it all the way over in M. So now it's going to be not this far. So I would normally want to draw it. I would want to try to, I'm going to change my color. Oh, well, let's see. I'll do it yellow. Normally you would think, well, it's going to be here, right? Because it's flipped over again now. But that's not true. Where it's going to be, I'm going to draw it in red. Where it's going to be is like twice the distance. It's going to be from here way over to here. It's going to be like I'll from here to here about I'm drawing it way out here. It's going to be parallel to these, but now it's going to be from here. It's going across M, so it's got to go the distance from M to say here, whatever that distance is. I had to draw that same distance over from M to here, and then that's the parallel line that's being drawn along. You get to see it now. So the R is back in the right orientation, but the distance that it traveled is very far. It's the distance from M, not no longer from L. Okay, that was kind of interesting. Okay, so example 3, it's composition of reflections in intersecting lines. So it says the lines A and B intersect in point C and form acute angle 1, with measurement of 35 degrees. Find the image of R for a reflection in line A and then a reflection in line B. Describe the resulting rotation. So the key to understand here is that the crossed lines give you the rotation. And what you're going to find out here in this bottom statement down here is that the distance of the rotation is going to be twice the angle between the two lines. So if there's 35 degrees in angle 1, your final rotation of R, in this case, is going to be 70 degrees. So let's look at it. So the first thing that's going to happen, you have the R just kind of happily sitting over here on the left side of angle A, of line A right here. Okay, here's R. So the first thing you're going to do is you're going to reflect R into the center here. So that's going to like bring it down. I'll draw the best I can, but it's going to bring it down like this. Okay, so that's kind of rotated it already. You see there's a rotation going on here, right? And then we're going to go across the other one to flip it back upright, back into correct orientation. And when we do that, now the distance from here to here is about this far. So the line, I'm going to say now, is a little bit of an angle going in. So it's about like that. And the R, okay? So we've rotated from the R over here, our line going up. This angle from here, the angle out to here, or actually to this outside edge from the total degrees. Yeah, no, I guess I did point to the right edge. Sorry. So if the angle here is twice the angle 1. So what you've done now is we've rotated the R across two cross lines with an angle of separation between the lines of angle 1 here of 35 degrees. And since we've done this move twice, we moved the 35 degrees and 35 degrees, the total distance we've traveled, and rotated R is 70 degrees. So what you're going to get is the angle between here and here. If you could get it down to the point, that's going to be a 70-degree change right there. Okay, and you see it way down here. So the reflect in A is right kind of same thing I drew, right? Reflecting A is down to here. And then we go across the B line. And now you see, look at the R is touching the line here. So it just does a flip over it. Doesn't even move very far. But the line, the R is going across this arc. It's traversing the arc. And that arc from blue line here, I'm going to do this in red because the blues are getting mixed up. From this line here to this line here is twice angle 1, which is 70 degrees. So R rotates clockwise through the angle shown in the green arrow, although I just drew blue on it. The center of rotation is C, and the measure is twice angle 1, or 70 degrees. Okay, example 3, check your understanding, is repeat example 3, but begin with R in a different position. So why don't you go ahead and try it. You can, draw up your cross lines. The angle doesn't really make much difference. It's just, we're not asking anything about degrees or anything anymore. It's just to see the idea of the rotation. So why don't you try it? When you come back, we'll try it together. Okay, now that you're back, I was trying to think of how am I going to try it. And I said, well, I think I'll do this. I'm going to say, so we're going to start doing the same thing over here. Although I'm going to draw my R like this. Okay, so here's my R. It's kind of like standing on the line. So the first thing I'm gonna do is I'm gonna flip it right here. So it's gonna come out here like this, and then it's gonna go around here. There's my R, the first flip right there on the line. Now the next time it's gonna flip is across B. Well, in order for it to flip across B, I'm gonna go out about this far, about that far. I'll do up here. Hopefully I'm getting this kind of correct. There. And that means that this is going to go, the feet are going to go down now, right? And it's going to go on an angle here. Let's say that it goes, I'm going to, let's see. I'm a little high on that dot. I'll go down a little high, lower. So it's going to go down like that, I'm thinking. And it'll come around here like this and like that. So now what happens? So now here it's back in its correct orientation. As good as I can draw. It's correct orientation, and it's moved. It flipped once, and then it flipped over the line down here. And we could probably honestly say that the angle that it moved, here's C, from here to here, is twice 1. I mean, I'm not a very good drawer. This freehand drawing for me is not coming out very good. I'm going to erase that line. Came out kind of not that good. But you get the idea, right? So it goes from here to this outside edge up there like that. And that's probably as close as I can get it. I wish I had a straight edge that I could use here. Okay? Okay, objective 2A, glide reflections. Two plane figures, A and B, can be congruent with opposite orientations. Okay, so that means they're congruent figures, but one's flipped, right? Okay. Reflect A and you get figure A prime. That has the same orientation as B. So now A and B are congruent figures with opposite orientation. So B is a flip of A. So we know that that's true. Reflect A and you get A prime. That has the same orientation as B because B is it's an opposite orientation of A. Said that in the beginning. So thus, B is, according to our theorems, 12.1, 12.2, 12.3, right? Mostly by 12.1. B is a translation or rotation image of A. So by theorem 12.1, two reflections map A prime to B. The net result is that three reflections map A to B. So with the two translations. We mapped A prime to B because that's what theorem 12.1, all these theorem 12.1, 2, 3 all say. So the net result is the reflection of A goes to B. So this is summarized in what is sometimes called the fundamental theorem of isometries. And the fundamental theorem of isometries. In a plane, one of two congruent figures can be mapped onto the other by a composition of at most three reflections. So as we talked about here, it takes two to get from A prime to B, and it takes one to get from A to A primed. So that's putting those two together, them flip from A to A prime, and the two flips or the two translations from A prime to B is three translations. And that's what they're trying to tell us here. Now, an additional fact as we move on, if two figures are congruent and have opposite orientations, but are not simply reflections of each other, then there is a slide and a reflection that will map one onto the other. A glide reflection is a composition of a glide translation and a reflection in a line parallel to the glide vector. Okay, so we're going to look at that next. Example 4, finding a glide reflection image. Coordinate geometry we're talking about here, right? So find the image of triangle TEX for a glide reflection where the glide vector is 0, -5, x is 0, y is -5, and the reflection line is x equals 0. So the image is here, the one on the right. You see, that's what we're going to be moving. We're going to be sliding and reflecting. Okay, so we start on the left hand side with TEX, and we're going to do first thing we're going to do is this glide vector, which is we're going to take 0 movement in x, but we're going to go -5 on y. So all three vertices are going to move 0 in x, but they're all going to move -5 in y. So that's what you see going on here. We went from E, let's say on the text, we went from E right here down 5. 1, 2, 3, 4, 5, down to this point. We took x and moved it down 5, a -5. We took this and went -5. That's for T. Well, we didn't do anything in x. We just went straight down. That's where we got the 0, -5. That's our glide vector. And then the reflection line is x equals 0. So x is 0 right here. This is x is 0, right? X is 0. And we're going to reflect across. For this lower triangle, we're going to reflect across. So that's going to put E, this is going to be E prime right there. And then we're down here out 2. This is X prime. And way over here is T. And so this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is T prime. So we can draw our triangle, which is right here. There. There. And try to get this one. There. So that is our triangle. So now you see the new image right over here. E prime, X prime, and T prime. And that one looks a little better than mine, but I think you can see they look somewhat similar. All right. Okay. Use triangle TEX from example 4 above, right? This is check your understanding for example 4. Find the image of triangle TEX under a glide reflection where the glide vector is 1, 0, and the reflection line is y equal -2. Okay, and the second part of this question is going to be critical thinking, right? Would the result of part A be the same if you reflected TEX first and then did the translation? And explain. So while you go ahead and pause the video and think about this, try to draw it up on your own, I'll wait for you. Okay, I'm assuming now that you're back. So here's what I've got going for us. I've drawn in the a little bit of the preparatory work for the reflection. But so what does it say? It says using TEX from example 4 above, find the image of triangle TEX under a glide reflection where the glide vector is 1 comma 0. So that's a move in X of +1, that's to the right, and no movement in Y. Okay, so that's what the reflection is going to be. But then we're going to reflect across Y equals -2. So I've drawn the line here. The red line down here right here. This red line is I'm calling -2 right here. So here's my 0. My origin is right here, and I'm using 2 squares for 1, right? So if there's 2 squares, this is their half. Each square is 1/2. So TEX is TEX, okay? So what do they want us to do? Find the image of TEX under a glide reflection where the glide vector is 1, 0. So what this is, X is 1. So they want us to move from here. They want us to move the E to here. And then 1, 2, 3, 4. We're going to move 2 this way, right? To here. And then this is going to be moved 2 right here. Nothing in Y. So there's our new triangle. I think I'll make that in gold. Try to draw it in so we can see it. Oops. It's hard to draw these. There. There. As good as it's going to get from me. Okay. So there's the translated 1 in X, 0 in Y, TEX. So we're not complete. So now finally we have to reflect uh, across line Y equals -2. So down here, I already told you that this is -2. Here's 1, 2. Okay. So here's -2 right here, -2. So now we're reflecting across that. So now we're literally on the line here. So this guy is from here, it's a long way. It's 1, 2, 3, 4, 5 up. So from here, we're going to go 5 down. 1, 2, 3, 4. And I can't get any lower. And I'm going to put this in red because I'm losing the color. Where's my pen? Where'd it go? There it is. Color, red. So the way down here is right at the very edge is E prime. Okay, E prime. So now we're going to bring down one out. We're going to bring this down from the -2 we're reflecting it. So it's 1, 2, 3. So 1, 1, 2, 3. Okay, so now this line goes from here to here and it's 1 out. So that's this guy. Oops, that guy there. And that is X, right? So that's X prime. And now we've got this one way out here and this bringing it down. And we're how many down? We're 1, 2, 3, 4 up. So we're 4 down right here. From here, 1, 2, 3, 4. So that would mean that the line's going to be here. And we have a line there. And this is T prime. So there's T, E, and X prime based on this example problem here, checking your understanding. So that's A. So what about B now? critical thinking. Would the result of part A be the same if you reflected it and then translated it? Well, the answer is yes, it would be the same, because if you what does it say? If you reflected it first, so reflecting it would be what? You would, instead of sliding it over, you would reflect it down, and this whole picture would have been, and this one here would have been here, right? It would have been here. Where's my pencil? Come on, pencil. There. It would have been here. I'm going to change colors. Let me do this in blue. It would have been here's where we would have started, and then we would have been up here, kind of a thing, right? So the point is, we would have flipped it first and then slid it over to where you had to be. Wouldn't have made any difference. You say flip it first and then slide it, or slide it and then flip it. It's absolutely no difference. Okay, objective 2B, glide reflections. You can map one of any two congruent figures onto the other by a single reflection. A single reflection. Translation, rotation, or glide reflection. Thus, you can classify any isometries. So the isometry classification theorem. There are only 4 isometries. They are the following. There's a reflection isometry, which is the one we're showing here where the line's in between them. We've got this line down the middle here, and you just take it, flip one over the other, like flipping a pancake across a line. And then there's a translation where this R in this case moves along a straight path to the orientation of the R didn't change. It just slid from one direction to another. And then there's a rotation where we took this R on a journey around a circle, and the R turned and is now pointing. It's made a change in its angle, right, from here to here. Okay. And then there's a glide reflection where it glides a certain distance and then it reflects across the line. Those are our 4 isometries. Okay, example 5, classifying isometries. Each figure is an isometry of the figure at the right. You see it here, it says spin with the little arrow on it. Almost looks like an Amazon logo kind of a thing. Anyways, tell whether their orientations are same or opposite, and then classify the isometry. Okay, so the same or opposite means flipped upside down or not, right? Okay, so we're looking at this spin. You see the way it starts out looking. So is the first one here, A, is it an opposite? Or, yes, of course, you can see that sine is spelled backwards kind of a thing, and it's like you're looking at it in a mirror, right? So, and it's a reflection, like in a mirror. It's exactly what they're saying. That's why it's a reflection. Then the B is also a mirrored reflection, but it's a glide reflection. So it means that it's moved. It's not in the same orientation. There's a glide and it's flipped. So you can see that it's not, if it was the first one, just the reflection, it's still the same orientation. It's this way versus this guy up here. The orientation still the same. On the second one, there's an angle change. It's still flipped, but there's an angle change. Now, when we look at C, they're the same. In fact, it's truly the same. The only thing that most it could be is a translation, because it went from up here in the corner. Let's say that it slid all the way from here all the way down to here. That's to keep that same orientation, everything. And then there's this, it's the same, except there's a rotation. So it started off here, and then it went around in a circle, and now that's the bottom, where the bottom was up here. Now its orientation is flipped, probably almost, what, 180, about 225 degrees or whatever it is. Something like that it rotated. Okay. Okay, example 5, check your understanding. Classify the isometry. So why don't you look at this? What do you think? What kind of isometry is this? Well, it's the 45 is not flipped on its belly, right? So it's not opposite by any means. And if it translated or slid in any way, it didn't slide without, I can't read it now, right? It's rotated. So at the 45, it was just a slide. I'd always be able to read 45 in its natural orientation, but it's like almost on its head, upside down. So this is a rotation. I'm going to write it right here. Rotation. Okay, that's it for this review.